Welcome to the presentation on linear algebra, specifically the day Tony missed of math. Oops, 120. I wanted to change color here. And at Kuka. Okay, so the first part of the lecture is actually really simple. There's nothing like you knew this before you took this class. If we have 2 points in space, F and another point G, and together they make up a vector where F has the points x naught, comma y naught, and G has the points x, comma y. We have we have another vector in space. I'm going to call it v, vector v, and on vector v there are the points which I just made up, r, and the endpoint here is, or the terminal point is k, and k has the points a, comma b, and we'll call this w just for namesake to make things easier. Now, all this is saying is that w is a scalar multiple of v. And that's fairly obvious here. If they have, because v and w, because if v is parallel to w, in other words, if the slope of v is the same as the slope of w, then they are just scalar multiples of each other, and that's going all the way back to grade 10 coordinate geometry, where we learned about slope and all that fun stuff. That these are just scalar multiples, and when we think of multiplication, we think of making bigger, but we can also make smaller. So v can just be a translation of w, and that seems fairly obvious to me, and I hope it seems fairly obvious to you. So let's turn this into some formulas. Actually, let's make this into something concrete. So we're saying that w is just a scalar multiple of v. And that makes sense, and this is fairly important, and anything I box is fairly important, so we might want to write down all of it, but you know. Okay, so and we have f minus g here, so f, and what is w? W is f minus g, and another way to write this would be f minus g equals lambda v. That makes perfect sense. That makes perfect sense, and I guess we could also say that this equals w. Okay, so what can we do with this equation here? Well, we can solve it for g, and g is equal to f plus lambda v, scalar multiple of v. And what does this resemble here? What does this look like that we learned way back in grade 10? Well, this looks like y equals mx plus b, doesn't it? Where y is g, and f is b, and lambda is m, and v is x. And this looks exactly like, and that's where that comes from. And you really don't have to know that, but that's just interesting to know that's where that came from. So this is also very important. So I'm going to box this. Okay. And from this equation, well, what can we do with this equation? What can we get from this equation? Well, if I said to you that what if f passed through the origin? What if f passed through the origin? Well, what would that mean? Well, what would that do to this equation? Well, what does that mean, first of all? If f passed through the origin, that means that f is equal to 0. And when I say f is equal to 0, I mean this f right here. F is equal to 0. Well, what does that mean for us? Well, or why does f equal to 0? Is it equal to 0 rather? Well, say I had a line here. Say I had a line with the points f and g, and I started at point f. And from point f, I hadn't made any prior steps, so I've made 0 steps up to this point, and we'll call this line w. Call this line w. And I keep walking, and then I stop at point g. Well, what is the value of w? Well, the value of w is g. because I've walked g steps, and that makes and that's, you probably never ever questioned that before, but that's what this origin means. So you could say f is your origin. F is your origin. Okay, so what would happen to this equation if this equation here is f passed through 0? Well, let's look at f. What would happen if f passed to 0? Well, this would just be g equals lambda v, because we wouldn't need to include this f in here, because it would be 0. It would be 0 plus lambda v. And here we can write, just as a little side note, that that f is equal to 0, which we already wrote up here. So that's nothing new. That's nothing too complicated here. We're just defining this in terms of different variables here. But what if we wanted to represent this right here in point form? Because in grade 10 we were able to represent slope in a point form. So let's define a couple of variables first. Let's say that f is equal to x naught comma y naught, which it is. We define that up top there, and I'll scroll back once I'm done writing all these and prove that to you. And g is equal to x comma y, and r, and this time r is equal to 0. And see, these were where we got this from, x naught, y naught, y, and then r is equal to 0. So we're going to say r passes to the origin here on this vector v. And I will highlight this just so we don't get these confused. Vector v. Okay, and k, as we see up there, is equal to a comma b. So can we derive a formula that links all of these together in the same fashion that we did up here? Well, yes we can, because g is equal to x comma y, and f is equal to x naught comma y naught plus lambda, because we didn't have any points for lambda, that was a scalar multiple that didn't have any points, plus v. Now you're saying, okay, well, why weren't we able to put v in terms of any point? Well, we can actually, but we have to do some thinking. We have to apply the same principle that if I had a point r, and I started at r, and previously, as I'm going to walk towards k, but previously, before I started at r, and I haven't moved at all. So the amount of steps I've taken is 0, and we'll call this vector v, because we're defining for v. Now I hadn't taken any steps at all. So as I walk towards k, how many steps have I taken? Well, I've taken k steps. So this v is equal to k. And what is k equal to? A comma b. So we can redefine this as x comma y, x naught comma y naught, plus scalar multiple a comma b. And this is really important. If you don't understand this is going to be very hard for you. You must understand. As you're walking, if you haven't made any steps previously, and you're walking toward, and you make a number of steps, say I made 10 steps, for example, well, how many steps have I made? Well, I've made 10 steps, and that would be, and this is a k, actually. I make my k's kind of weird. Then that would be how many steps you took, and if you just really have to grasp onto that there. So if that's hard for you to visualize, get a permanent marker and write r and k some space away, and start at r and count how many steps you take to k, and then draw a line between them, and then you'll understand that the value of that line is just the amount of steps you've taken, and therefore is where you ended up at k. Okay, so with this, so now we have this equation. This equation is the point form. This is the point form of this yellow equation up here. These are the exact same equations, except they deal in points, except the other one deals in points. So that shouldn't be too strenuous for anybody. No, but here comes a little bit of new information. So this equation is called an implicit equation, and what that means is the variables are not all collected on one side or the other. They are distributed up. So we have defined in terms of x and y here and x and y here, because usually when we look at equations we have x equals y, or y equals mx plus b. There's y on one side and the rest of the variables on one side. But this isn't defined in terms of any one thing. So this is called an implicit equation. And what other type of equation is there? Well, there's an explicit equation. And the difference is you can think of it as say I said to you, wow, I haven't eaten in a while. Well, what does that imply? That implies that I'm hungry. And what if that's implicit. And explicit is, say I said to you, I'm hungry, let's get something to eat. That is explicit because I've explicitly said to you that I'm hungry. So that's the difference between that. So is there a way that we can explicitly define an implicit equation? And the answer is yes, there is. They are called parametric equations. And yes, we could just solve this for x or y, but what would we do? What operation would we use to break up an ordered pair? Well, you can't, because it's an ordered pair. They must stay together. So in this case we must use parametric equations. And these are explicit equations. And what's going to happen is we're just going to take the x value and the y value from every one of these points. And I'll show you how we're going to do that right now. So we're going to say x is equal to x naught plus lambda a. And we're going to, and that's fairly obvious. We took the x value from here, the x value from here, the lambda from here, and the a from here. And if this doesn't make sense, if it doesn't make sense to you why we carry through this lambda, please review your rules of vector multiplication, because that's very, very important. This is the distributive rule. And now we're also going to take the y value of this. We're going to say y is equal, so we're taking the y from here, the y naught from here, the lambda from here, and the b from here. And the reason this lambda occurs twice is because of those vector multiplication rules. So if you don't remember that, please go back and review that. So these are our explicit parametric equations. And what do these mean to you? Because when you back in grade 10, when you went to graph things on your graphing calculator, you could only graph in terms of y. But for this x, there's no y value here, so you couldn't even solve to graph for y. So what does that mean? If you were to throw this into Mathematica and tell it what it was a parametric equation, it would look at it and say, okay, for all x values, I'm graphing this, and for all y values, I'm graphing this. And then it would graph the same thing as it would if you were to take this and take a long time and graph that by hand. So this is part A of the lecture, and I'm splitting this up into 3 different parts because I don't want to run out of time, and I don't want to end up with a monster huge file to upload to YouTube, and it only lets me upload 10 minutes anyway. But I will be back, and we will see you in the next presentation.